Okay, so now we're going to talk about Communicator's implementation of shattered mode. So the way that we approach shattered in Communicator is we use an XML description file. And this XML description file can be generated either on the server or on the client. So this provides maximum flexibility for how you want to bring your shattered model into Communicator. So when we say that this can be generated on the server, what we mean is that at the time of conversion of the models, you can create an XML file using Hoops Converter, or you can write your own XML file as long as you follow the specified format. Now, on the client, you can build up an XML file, and you can then send that into the viewer, and we will handle pulling all of the files in and creating the shattered assembly from the XML file. So both the server version and the client version use the same XML specification. The only difference is where this XML file comes from. So we'll talk a little bit more about what this XML file contains, and then we'll talk about how it actually kind of works to create the shattered model. So the XML file contains the entire model structure for this new shattered model you're going to be building up. So if we look at the example here, we can see we have a root file, a root element, and then we have a model file. And then in that model file, we basically describe the entire assembly tree. And this assembly tree that we're building up, instead of just being created from parts in the same model file, is created from different models themselves. And a couple things to look at here. Now, we specify the name of this node in the assembly tree, the topmost node for this model file. So in this case, we're talking about a model called MotoX. And then we need to specify, this is important, we need to specify the relative transform of where we're going to put this model in the scene. Okay? So if we just dumped all of the models in themselves, remember, these are all now individual models. They know nothing about each other. If we just dump them all in the scene, they're all going to be about the origin because they have no concept of the other models. So if we converted this model in a monolithic mode, we would read where all these parts go, and we place them correctly. But in shattered mode, we have to specify where each part goes in the scene. Okay, and then we have to specify what children are going to be of each one of these nodes. And that's also important because remember, this is a relative transform. So the transforms are going to inherit from each other. Now, in practice, if you're using Hoops Converter to generate this file, we will figure out all of this for you and create this XML. However, if you're using your own system to assemble these parts, then you'll have to make sure that the transforms are specified correctly. Now, we also specify different attributes that we're going to attach to each part. And again, like this is done automatically by Converter, but you're free to attach whatever metadata that you want to each part. So what the result is a complete XML file that describes the structure of your model file or your shattered model file. And now we want to take this XML and actually use it to glue all these parts together. And this is where we have, again, two paths to do that depending on if you're creating this on the server or the client. So we'll talk first about how we glue this together on the server. So Hoops Converter can take as input one of these XML files that describes all your parts. Okay? And then what it's going to do is it's going to parse this XML file and pull out all of the model files that it needs and all of the transforms that describe where these models are going to be placed. And what comes out of that is what we call a master model. So a master model is an SC model just like any other model, except it doesn't contain any geometry data. All it contains is transform info and links to the other model files. So what this means is that this model file, when it's loaded, is, think of it as just a collection of symlinks. When it's loaded, it's going to just reference the other model files to get the geometry data, and it's going to load them into the scene using the transforms that you specified. So what this essentially means is that as long as the names don't change or the positions don't change, you can swap out model files as long as they have the same name. So for example, that I talked about earlier, we have this motorbike, maybe the handlebars changed. As long as the handlebars are positioned in the same space in the world, and you don't rename them, you could just switch out that model. So you can say, okay, maybe I replace the old one with this new revision, and if I reload the model, it will pick up that new revision. And you don't have to reconvert the entire model. Like in monolithic mode, you have to redo everything. But in the shattered mode, we can just simply swap the file. Now this is really cool, but there's some things that we have to think about. So if for whatever reason maybe the handlebars are now bigger, they exist in a different position in the world, we will have to regenerate this master model because the transform changed. However, the thing that's good about this is that creating this master model is a very quick operation. Really all we're doing is parsing this file, this XML file, and then writing out some symlinks. We're not actually writing symlinks on the file system, but symlinks in this file, basically. So even though we changed the handlebars and they are in a different spot, we can quickly regenerate this master model and then reload that scene and see our change. So the win here is that for very large models, it gives us a very granular ability to change things without having to pay a big price to see those changes. Now, it's not all fine and dandy. There are some things that we have to think about when we're working in a shattered mode. So, for example, we have to make sure that all of these models that we need for our shattered mode are available to our viewer. So instead of working out just one SC file, we could be working with 10, 100, or 1,000. So we have to make sure that all of these files can be read by our viewer application. So what this means is that if we're storing these in different file systems or databases, we have to make sure that we can get all of the required files in one location in order to stream it. So this does pose some challenges with very large models and different web storages. We'll talk about how we store models in different cloud scenarios in the later module when we get to the server. But just know that when working with Shattered, managing all these models can be a little bit tricky. So we'll talk about ways to approach that tomorrow. So now that we know kind of how a master model works, we'll talk a little bit about how we dynamically build this assembly on the client. So again, it's the same idea. We have this XML file, and what we're going to do is there's a method on the web viewer to dynamically load these shattered XML assemblies, and when we feed this XML file into the client, what's going to happen is behind the scenes, we're going to send that data down to the server, and in essence, what we're doing is we're creating one of these SC master models kind of internally in the system on the fly. But all the same rules apply. When we send this model down, or when we send this data down from the client to the server, all those models still have to be there. It's just, it allows us to kind of create this SC master model concept. We're not actually creating one on the fly, and it gives us a little bit more flexibility. So I'll talk a little bit about how we create these using Converter, and then I'll show an example of what it looks like in practice. So like I mentioned before, creating a shattered model is a two-step process. First, you have to convert all of the parts and create this XML file, and then you have to create the master model that glues it together. So we've tried to make this as easy as possible in Converter, but by adding these two command line options, so preparing the shattered and then inputting the XML shattered. So the first step is we need a model that consists of multiple parts. So for example, if you have like the motorbike or a micro engine, something along those lines. And what you're going to want to do is you're going to want to tell Converter to prepare the shattered XML file. And then you're going to want to tell it where it's going to prepare the shattered parts. So what this means is that when it reads in that micro engine, instead of creating just one model for it, it's going to create one model for each part. And we just tell it where we want that folder. Okay? And then, in order to actually create that master model, we're going to tell it, okay, we want to input the XML shattered, and this tells it, okay, your input is not a CAD file, but it's this XML specification. And then we need to tell it where it can find all those parts that are described in this file. And then we simply tell it to output the master model. And then it's going to do exactly what I described previously. It's going to create all those links to each file and then create the master file.
Okay, so let's take a look at how this would work on a file system. So on the right-hand side here, we have a sample assembly, and it's a pretty simple assembly, but it'll help illustrate the point we're going for. So in our sample assembly, we have two different colored boxes connected by these arrows. Now, the blue boxes represent all of the files that are in the original assembly. Now, this consists of .asm and .prt files. And the green boxes represent the files which we've converted into our streamcast format. So remember that these complex assemblies are broken up into part-level components. So in this case, we have 7 streamcast files that are going to be combined to create this shattered model. Now, our XML file needs to have an entry for every node in our model tree. So we can see in the diagram that we have these arrows that connect the different blue nodes and specify the parent-child relationship in the assembly. So for example, we can see our topmost node, 1.asm. This has 3 children, 2, 6, and 11. Now, these nodes in turn have their own children. So 2 has children of 3, 4, and 5, and 6 has children of 7 and 8. Now, 11 is just a node that does not have any children. It's a part file. And you can see here that this part file has the corresponding stream cache file. Going further down the tree, we can see that the deepest nodes are the children of 3, which are 9.prt and 10.prt, which in turn have corresponding SCZ files. So the thing to kind of take away here is that all the leaf nodes of the tree will be part files that have corresponding SCZs. And when we create this XML file, we need to make sure that every part file has an external reference to an SCZ file. Now, how does this allow for quick reconfiguration of the model? So you can see here, like for example, if we took part 11 and something about this part changed, all we would have to do is reconvert the new 11.prt file and create a new 11.scz file. Now, in some cases, if this model didn't change size or location, we can reuse our existing XML file or SC master file that we've created, just replacing the old SCZ file with the new SCZ file, reload the page, and we would see those changes immediately. Now, if something about that 11.scz file changed in the sense that maybe it was made bigger, made smaller, or its position was changed, we would have to update our XML file, which would specify a new relative transform for that part. But thinking back to what we talked about previously, the overhead of creating these XML files or creating a new SC master file is low. So moving this around in the scene wouldn't require a reconversion of the entire assembly, which if it was hundreds or even thousands of parts would take a long time. So you can see here that this workflow provides the flexibility we need to update parts quickly without having to pay the cost of reconverting the entire assembly.